So I'd like to welcome the first of our speakers, bringing in the topic of quantum mechanics. We have Athanasios Tzemos from the Academy of Athens in Greece. And Athanasios, if you would care to share your screen, please. We see your screen. I can't hear you yet.
Can you hear me now?
That's great. Thank you so much.
Perfect. So everything is okay.
That's good to go.
So, hello from Greece. I'm Athanasios Tzemos from the Research Center for Astronomy and Applied Mathematics of the Academy of Athens. And it's my fourth consecutive participation in the Maple Conference. I work with Maple since I was a pre-graduate student back in 2005. And here I'm going to show you a very brief report for our research conducted in our center, which has a long tradition in-house in astronomy and general in nonlinear physics. So, house in interacting oscillators, a classical and a Bohmian perspective. So, Bohmian quantum mechanics is an alternative interpretation of standard quantum mechanics. It's a trajectory-based quantum theory which predicts the same results as a standard quantum mechanics that we know from the university. And its origin comes back from the very first work of Louis de Broglie. So sometimes you can hear it as de Broglie-Bohm quantum theory. In Bohmian quantum mechanics, the quantum particles are guided by the wave function, the usual wave function that we know from standard quantum mechanics, the solution of the Schrödinger equation. So, according to this theory, each quantum particle follows a deterministic trajectory, which is guided by a set of first order in time differential equations, the so-called Bohmian equations, which are of this form. And from the very a quick view of these equations, you see that we have this denominator, which is the squared modulus of the wave function. So, in standard quantum mechanics, there is no straightforward definition of chaos, since in standard quantum mechanics there are no trajectories. From classical mechanics, we know that the system is, in general, chaotic whenever a very small, a tiny change in its initial conditions has a very drastic results. So, two very close initial conditions produce quite different time evolution for a certain dynamical system. Bohmian quantum mechanics allows us to use the traditional, this classical and traditional definition of chaos and try to understand what happens in the quantum realm with all the arsenal of classical dynamical system theory. There is a huge debate, if you like quantum mechanics, about which interpretation is correct. All of them predict the same results in principle, but they have a different view of the quantum phenomena. Okay. In Bohmian quantum mechanics, chaos is produced whenever a Bohmian particle, a quantum particle following the Bohmian equations, comes close to a nodal point. The nodal point is the solution of the equation psi equals 0. So at the nodal points, the wave function vanishes. So exactly on the nodal points, there is the probability of finding a particle is 0. So the nodes play a crucial role in Bohmian mechanics since they are accompanied in general by hyperbolic points, the X points. We found them back in 2007 and then formally in 2009 in our center. These X points are stagnant points, fixed unstable points of the Bohmian flow in the moving reference frame of reference of the moving nodal point, and they scatter the particles and produce chaos. Together, the nodal points and their fellows, the x points, form what we call a nodal point x point complex. So this is the general picture. Whenever a trajectory comes close to a nodal point, here we have psi equal to 0, then we have very close to the nodal point its fellow, the x point, which is unstable. It has a stable and unstable invariant curves, as in classical dynamical system theory. And whenever a trajectory comes close, it gets scattered in this way or in that way. Some of the trajectories enter this narrow channel and they have access to the nodal point. Those trajectories are going to form what we call in Bohmian quantum mechanics the Bohmian vortices. So you see a vortices curve around the nodal point up to a time where the nodal point, which is a mathematical point and not a physical point, goes with an abrupt velocity to infinity, and the physical particle cannot follow it anymore. So one of the main questions about Bohmian quantum mechanics in general in quantum the framework of quantum foundations is, if we have a classical Hamiltonian system, okay, that we know how to study it, we know all the techniques, we can use the Poincaré surfaces of section, we know the Lyapunov exponents. In general, we are very comfortable to make calculations about its chaotic dynamics. What are the similarities and the differences between Bohmian and Hamiltonian chaos? So if you take a Hamiltonian of this form, which is nothing more than a 2D harmonic oscillator plus a perturbation, epsilon x psi squared. Okay, so what does classical mechanics tell us about chaotic behavior and what Bohmian quantum mechanics? In order to proceed, we have to form a coherent wave packet. In quantum mechanics, a single quantum particle has no single energy. The closest form of a wave function to that of a classical particle is that of a coherent wave packet. Okay, so if you take a coherent wave packet, you see it has some dispersion around the classical object. Then the perturbation is going to break its coherence in time dynamically. So what we found with Maple and with Python, with joint work, is that all of its trajectories, the Bohmian trajectories, the trajectories that follow the Born rule distribution according to this wave function. So if you make a Born rule realization of this wave function with, say, 5,000 or 10,000 particles, then you are going to see that all of them in the long run are going to be chaotic. Something that is not true for the classical system. There you have stability islands and chaotic zones. But in Bohmian quantum mechanics, what we found, and this was published about 1 or 2 years ago, I don't remember, is that all of the trajectories are going to be chaotic in the long run, but with a catch. The trajectories are all going to be chaotic in the long run, but the time that chaos enters is inversely proportional to the perturbation parameter. And this is actually the only similarity with classical Hamiltonian chaos. Bohmian quantum mechanics is not a Hamiltonian theory. Okay, it looks like Hamiltonian theory. It can be casted in a Newtonian form, but we do not use a Hamiltonian form for the dynamical system. Okay, so this coherent wave packet consists of many different energies. okay, of the harmonic oscillator with the usual Hermite polynomials that we know from standard quantum mechanics from the university. In time, this the constituents of the coherent state change their contribution, and some of them have stronger and some of them have weaker contribution in time. So in the long run, all the trajectories become chaotic. Here you see what happens for a fixed time if we have a small perturbation, a medium perturbation, and a strong perturbation parameter. You see that here the coherent state is almost unaffected. Here we have a larger deformation, and here we have a much bigger deformation. For a fixed time, imagine that this changes at every time. And here we have plotted the nodal points of the wave function. Here you see that most of them are away from the Born distribution. Here some have entered its valleys and have deformed actually the Born distribution, and here you have even greater deformation with many nodal points and their fellows, the X points, which are always close to them, coming here and scattering the incoming trajectories. So the general picture is that in Bohmian quantum mechanics, that many of the trajectories that are used to be Lissajous figures in the absence of the perturbation parameter, now you will see that they are going to be chaotic, but after very long time, a time that depends on the perturbation parameter. And here you see a typical Bohmian trajectory for a small perturbation, and here for a strong perturbation. And here you see the number of chaotic trajectories in the Born distribution for this case, and the number of trajectories in the Born distribution for this case that are going to be chaotic. Here, House enters, most of them become chaotic. Here you see the 100% at about 150 time units, but here about 2000 units. And this is the only similarity with classical house that we know from standard Hamiltonian dynamics. Here you see that we have plotted with Maple and Python the Poincaré surfaces of section. For small perturbation parameters, we see that order dominates the Poincaré surface of section, and then the section, as we increase the perturbation parameters, starts to get deformed, the stability islands break, and gradually we have a formation of chaotic zones. And here House enters very clearly. Here it is absolutely dominant, and here in the orange region we have escapes. We have such a ratio between the perturbation parameter and the energy that most of the trajectories escape to infinity. Okay, in Bohmian quantum mechanics we have no escapes to infinity, although it is in principle allowed, but in practice we never find them, because the psi squared is always such that it is trapped in a certain region, and psi squared is a pilot wave and it guides the Bohmian particles. So it is extremely improbable to find Bohmian particles far away from the center of the configuration space. And here you see, what we see is that the area covered by the chaotic zone, the area as a fraction of the total area of the Poincaré surface of section, follows this curve as a function of epsilon. So after epsilon 0.08 or 0.09, House becomes dominant. We found that in this case, the time that the Bohmian trajectories become chaotic is very close to this one. So summary. House is generated in both cases by unstable points. The X points in Bohmian mechanics and the usual unstable points, which are projections of the unstable periodic orbits in Hamiltonian dynamics. The unstable points in the classical case are dense, while in the quantum case they are in general separated, and we can find them one by one. The quantum unstable points that produce most of House are the X points near the nodal points. A minor role is played by the unstable points of the inertial frame of reference and not of the moving frame of reference. These are called the Y points, and actually I showed some of them in the previous Maple conference. But the mechanism is, in general, the nodal point X point complex mechanism. In the classical case, near every unstable point, there are unstable points of higher multiplicity that overlap. This is the resonance overlap mechanism, well known back from the 50s and the 60s, which produces House in classical Hamiltonian dynamics. In quantum systems, there is no resonance overlap in Bohmian quantum systems, and most trajectories for epsilon for non-zero perturbation parameter are chaotic. We found no ordered trajectory in the log run. There is only a difference in the time when the chaotic character of the trajectories is established, and this seems to be connected with the area of the chaotic zone of the classical Poincaré surface of section. But this is we are making. I think that we are still making progress in understanding this special topic.
Thank you, Athanasios. I think we are actually pushing the edge of time now. So
perfect.
I think your conclusions were a nice summary. Was there any last comment before we move on to question?
No, I have no.
Thank you. So it's quite unusual to see just how much this is progressing in society today, with a lot of cases where the new innovation like molecular modeling, nanoscale engineering, designer, they are often looking still at the probabilistic waves rather than well-defined trajectories. Do you think that this has applications there as well as in astronomy and astrophysics, that the trajectory path would be becoming more popular?
Yes, actually, the Hamiltonian that I see you is the so-called Boses and Kontopoulos potential, which is very frequently used. It started from astronomy and found many applications in quantum chemistry, this Hamiltonian. The chaotic behavior of the classical system seems to have a huge effect in the quantum properties, both in the standard quantum mechanics that we are not doing here, and now we are trying to understand what happens with Bohmian quantum mechanics. This Hamiltonian models very frequently intermolecular interactions.
That's amazing. Yeah.
It's not about astronomy or quantum mechanics or anything. It's about dynamical systems. They are very they look very common, and all the techniques are the same. So whether you like to call it a galaxy model with just another component in the perturbation, you make it a galactic model, the Henon-Hiles model. And without this term, you are going to make quantum chemistry. It's all the same.
You got it. Well, thank you again, Athanasios, for a great presentation. Just a reminder, we will be moving on to the next speaker now, but just a reminder, if you have any questions for our last speaker, please put them in the chat and he will hang on for a little bit and probably reply back to any of those angles as well.
Perfect. Thank you very much.
Thank you again for your time. And if you could just unshare now your screen.
Okay, perfect. Excuse me, pause sharing. Okay.
That's great. So just a slight change in the scheduling right now, but we are moving on to one of our next speaker, Athanasios Paraskevopoulos. He will be, he's also actually from the Academy of Athens in Greece. Athanasios, if you would like to share your screen, are we still showing? Still showing the last speaker. So if you could unshare that one. Great, thank you. And good to go with the next presentation. We see that nice. Thank you.
Okay. Hello, everyone. My name is Athanasios Paraskevopoulos. Today, I will present you my work on an application of the unified transform to the one-dimensional heat equation on the half-line. This work is a part of my ongoing PhD research at the Academy of Athens, and it applies the unified transform method, also known as Foucault's method, to classical parabolic partial differential equations. Here is a quick overview of what I will cover. First, I will explain the motivation and give a short overview of the method. Then I will describe the Fourier transform formulation and the so-called global relation. Next, I will show how the integral representation of the solution is obtained. I will then discuss an example problem that illustrates the method in practice, followed by some numerical results from Maple. Finally, I will conclude with a brief discussion and future directions. The unified transfer method generalizes classical techniques like the Fourier and Laplace transform. It was developed by Athanasios Foucault to handle boundary value problems for partial differential equation on finite or semi-infinite domains. Traditional transforms methods often struggle with mixed or non-standard boundary conditions, and the Foucault method provides an integral representation that remains valid for any combination of boundary conditions like Dirichlet, Neumann, or Robin. This, this makes it particularly powerful for analyzing problems like heat conduction when boundary behavior plays a critical role. Now we consider the one-dimensional heat equation on the half-line. Then we prescribe one initial condition and a boundary condition, as we can see. So the task is to find the solution U for all x is greater than 0. Although this looks simple, the challenge lies in ensuring that the solution representation satisfies all these conditions simultaneously, especially when we work in the spectral domain. To derive the solution, we start by taking the Fourier transform of the equation, but only on the half-line. The half-line Fourier transform is defined from the formula over here. Applying this transform to our PDE and using the properties of the derivative, we find this formula. And this equation couples the transform variable u hat with the boundary values. Solving this equation leads to the global relation, which plays a critical role in Foucault's method. This relation connects the initial data u0 with the boundary data j0 and j1. It's the central analytic bridge that allows us to eliminate unknown boundary terms later on. Next, we analyze the analyticity and decay properties of the integrand. We look at the exponential factor. Its magnitude depends on the real and the imaginary part of lambda. So, for the integral to converge, we require that the absolute value of the real part of lambda to be bigger than the absolute value of the imaginary part of lambda. This defines a wedge-shaped region in the convex plane, typically called D+, where the real part of lambda squared is less than 0. By working within this region, we can safely deform our integration contour for numerical evaluation. Using now the global relation and the analyticity properties, we can derive the integral representation for the solution. The solution can be written as this equation here. The first integral is a Fourier inversion of the initial condition. It's what you get from the classical method. And the second integral is the new term introduced by Foucault's method, and it forces the boundary condition automatically. To make things specific, let's consider an example. We solve the heat equation with this initial condition and boundary condition. The Fourier transform of the initial data and the transform of the boundary data after a bit of algebra is the following. This can be substituted directly into the integral representation to compute the solution U. For numerical evaluation, we need to integrate this expression in the complex plane. The integrals can be computed along different contour deformation paths. In this work, I tested two strategies. The first is the ray contour. For this specific example, it's also possible to derive a semi-analytic expression for this solution by evaluating the integrals using the residue theorem. We find this formula here, where U1 satisfies the homogeneous part of the equation. This term captures the interaction between the oscillatory boundary and exponential initial data. In my second try, I tried the trapezoidal contour. I tried to avoid the simple poles on the boundary of D+, and the solution reduces to this formula. Now I tried to validate these results in Maple. I used for numerical implementation adaptive quadrature methods. The key verification steps are the following. I checked that computed solution satisfies the boundary condition. I am confirming also the initial condition and verifying numerically that also satisfies the PDE. The results show excellent agreement in all cases. Here you can see numerical plots of the solution U for several values of T. At short times, the heat distribution remains localized near the boundary, but as times increases, the oscillations propagate into the domain and gradually decay due diffusion. Both ray and contour, both the ray contour and the trapezoidal contour yield results that are identical up to machine precision, confirming the numerical robustness of the unified transform. To summarize the verification, we take the initial condition and we can see that is recovered exactly. The same happens for the boundary condition. Also, the PTE satisfied holds point-wise within numerically accuracy. The unified transform provides a fully consistent analytical and numerical solution. The Foucault's method provides a unified framework for solving initial boundary value problems on finite or semi-infinite domains by combining Fourier analysis with complex contour deformation. It produces integral representations that are both exact and numerical stable. In this study, we showed that both ray and trapezoidal contours lead to identical identical, highly accurate results, even for oscillatory boundary data. This confirms the robustness of the method and its potential for extension to more complicated geometries and equations. Looking ahead, my future research will extend this approach to linearizable PDEs and multi-dimension geometries. And I would like to acknowledge Dr. Konstantinos Kalimeris at the Academy of Athens for his guidance and supervision. I also thank the Maple Primes community, in particular Aker, Robin Rostamian, and Dr. David Harrington for their helpful discussions on numerical implementation. And finally, I want to mention that this work was inspired by examples from Athanasios Fokas' book, Modern Mathematical Methods for Scientists and Engineers. Thank you very much for your attention.
Thank you very much, Athanasios. That was a really good overview of the Fokas method. Is quite elaborate now. Just in the last 20 years, it's changed quite a lot. I'm just checking the chat, and there is one question that's come in that relates to just another method that you didn't discuss. Just in the interest of time, perhaps you would be willing to just jump into the chat and answer that live in that, and we will just keep us moving with the next presenter. But I appreciate your time and a very thorough overview of such a deep work. Thank you again for your time. If you could unshare now, we'll just move on to the next speaker, but please also check out that chat question. Okay, so we'll be moving on next to Marcin Kaminski from the Łódź University of Technology in Poland. Marcin, if you are available now, please share your screen and start your presentation.
Hello, good afternoon. Do you see my presentation?
Yes, we see this first slide now. Thank you.
That's fantastic. Thank you very much. Ladies and gentlemen, I would like to present a little bit my approach and my analysis made in Maple. This is called entropy-based uncertainty quantification in reaction-diffusion systems and problems with the use of the stochastic finite difference method in Maple. We programmed and we made a lot of different computational experiments together with my colleague, my past PhD, Dr. Rafał Leszek-Kosowski. We are from Łódź University of Technology, and this presentation and this work has been done in the framework of the research grant from National Science Foundation in Poland. I would like to say a few words of introduction, motivation to deal with this problem, to demonstrate you diffusion, reaction, and some basic equations, to tell about information entropy and telegraphic shortening, to demonstrate a little bit uncertainty in computer simulations, and to present some numerical examples. I would like to mention, by the way, and thank very much Maplesoft for some contribution to my conference, International Conference in Computer Methods Mechanics. It was this July in Łódź, and we are in preparation of the next conference, Emerging Trends in Applied Mathematics and Mechanics, also in Łódź, the same building, the same faculty, so we would be interested in promotion of your software too. As a few words of introduction, I would like to say that there is, of course, a lot of uncertainty in physics and biology and in the materials. We test uncertainty and quantify uncertainty in structural mechanics at my faculty, as well as in homogenization of composite materials. So the methodology I present is very general. Maybe you all know that most of uncertainty approaches is based on traditional moment-based technique or moment-based approach. Some people calculate, determine Monte Carlo simulations and some other techniques, expected values, variances, coefficients of variation, higher order statistics also. And this is very complex, because if you'd like to convince the people, and specifically the students, you have a lot of different statistical measures. we would like to present some alternative, a single approach based on Shannon entropy, and also some relative entropies and probabilistic distances. So the final results could be presented using a single graph. I think that there is no need to, let's say, demonstrate the physics and discuss the physics of diffusion in different media, starting from the mixtures of gases and solids and liquids, and also some other case studies like molecules in the gas. This phenomenon is described by a single differential equation, which in the very simple case can be described in one dimension with the following second order partial differential equation. And we would like to analyze, in this case, random concentration of certain molecules embedded into this system. And needless to say that we analyze this problem and this equation, taking into account that we cooperate with environmental engineering department, and we would be interested in cleanliness of the air. Therefore, let's say diffusion process is very, very important from the technical point of view. The boundary conditions may be, of course, quite different. Nevertheless, we need to assume, let's say, a derivative with respect to time equal to 0 at the beginning of this process, and d as the constant is for simplicity taken as 1, but maybe adopt to some, let's say, specific case study. Entropy is something known from thermodynamics. At the time of beginning of statistical thermodynamics, you remember Boltzmann constant and the second law of thermodynamics. Later on, entropy has been generalized to some probabilistic entropy as the measure of uncertainty or disorder in the given system. So it is a little bit out of thermodynamics, and probabilistic entropy became popular due to computer science people to quantify chaos in some, let's say, computer science systems, also the files, but it is also famous and available in physics, in environmental engineering, and civil engineering also. Basic definition is if we have n as the total number of the states of a given system, we pre-multiply probability of any possible state with its logarithm, and summation gives us the entire Shannon entropy. So, of course, the higher entropy, the more uncertainty and the more randomness in your system. So we would like to predict randomness in many engineering, let's say, case studies. And in engineering, we usually deliver some discrete description of our problem. This is finite element method, finite difference method, or finite volumes method, depending upon the specific application. And here we use spatial discretization using the grid, typical for the finite difference method. This grid and finite differences have been implemented in the system Maple. So some material and geometrical uncertainties can be treated as random parameters, but we can see also uncertainty during solution process, or to treat numerical discretization or general numerical error as the additional source of uncertainty. The problem is that we need to employ Monte Carlo simulation. This has been implemented in statistics library. And additionally, we need to process this final histogram of some diffusion constant or diffusion function using some additional functions inherent in Maple. This is specifically function totally into, so we can subdivide and to calculate entropy directly from having the histogram. Okay, so as a step number 1, we solve partial differential equation. Fortunately, in this specific case, we have available analytical solution for a comparison. Step number 2 is polynomial approximation using several solutions of the same differential equation. We can employ least squares method with different approximating function. This is also curve fitting library and curve fitting, let's say, function additionally in Maple. That is the case. And finally, we can use with statistical library Shannon entropy calculation. I mentioned, I think 2 or 3 years ago during the same conference, that it would be very nice to make implementation of Shannon entropy in statistics library. This is, it has been implemented in some other library of Maple. Nevertheless, it will be very nice. So finally, we can build using plot some analysis for the resulting Shannon entropy while increasing expectation or coefficient of variation of our input uncertainty source. So we can check what is really necessary to be treated as uncertain in the given problem. So additionally, we use some simple time series. One of the presentations during the conference was dedicated to Gompert's law for biological technical populations. We have a very similar time series, which is additional problem in our system. So treating of this, algorithm in Maple to treat this problem is the following one. We compute sequentially our, let's say, system of difference equation, and we also deliver computations of probabilistic moments, histogram, as well as the entropy in our system, and this is delivered in some time increment, let's say, machine. So this is our difference equation to be solved. There is no numerical problem with the stability. Nevertheless, in terms of randomization, we need to be very careful with discretization of the input randomness source. And some results, if you look over a diffusion process and expectation of diffusion function with respect to time, we need to plot it in different times moments relevant to our diffusion process progress. And we can also plot the same as both function of time and space. So to see some visualization of, let's say, random process of diffusion for different input coefficients of variation of our variable. Okay, we can then make a comparison of the Shannon entropy versus coefficient of variation. Both left and right diagrams demonstrate uncertainty in your system. As you see, a discussion of the uncertainty based on coefficient of variation is a little bit difficult because no specific pattern is obtained at the very end of your simulation, while discussion of an increase of Shannon entropy in both time and space is relatively easy, provided that you are able to make this implementation. So instead of many moments, we can discuss just uncertainty as it is. We can make similar analysis in terms of higher order statistics. This is just, by the way, a result of the study, like skewness of the concentration of the diffusion process, as well as the kurtosis of the same process, to see whether the resulting processes or variables may be similar to Gaussian distribution.
We're just at 12 minutes now.
Yes, and as a conclusions, I would like to say that we've studied a lot of applications of Shannon entropy computation, both to solid mechanics plasticity and some computational fluid dynamics, including diffusion. And it seems that this is a relatively novel tool for uncertainty quantification, specifically in computational mechanics. This is promising because as you've seen, determination of classical moments may be a little bit complex and not always gives you a good reasoning for statistical analysis. This is more or less everything I wanted to say. We, of course, plan to make some other computational implementations, hopefully using Maple software. Thank you very much.
Thank you, Marcin. It's been great to see how your work has progressed using the variety of packages and things with Maple as well, as well as the symbolic and the numeric all together. Really, really good package. If anyone has a question and would like to unmute themselves to ask it, we'll just check in there. Marcin, there is also a chat question that if you would mind maybe just answering that live in the chat. It just asks.
Yeah, thank you very much. Yeah, thank you much. I will answer for sure. Thank you.
That'd be great. Okay, we'll next move on to our next speaker, Dr. Thierry Dana-Picard from Jerusalem College of Technology in Israel. We've actually heard a little bit from Dr. Dana-Picard through the Maple transactions that were published earlier this year. So it would be interesting to find out his next step. Thierry, if you would be kind enough to share your screen and unmute yourself to start your presentation. We see your first slide now. Thank you.
Okay. So here. Okay. Thank you very much. It's an honor to be here in this conference. Actually, my name is Thierry Dana-Picard. This work is a joint work with one of my students, Daniel Tsirkin. And what I will show, it's a part, and as you told, the first part has already been published in the Maple transactions, and hopefully the next one will be submitted next week. Actually, this is a part of a more extended domain of interest for us, and not only for us, but only for other colleagues who began joining us. And we have a lot of motivations for that. There is a motivation purely mathematical, because we have here an interplay between geometry and algebra, and this is the basis of all the field of automated proofs and automated methods and so on. But actually, it's also because things are very nice. And I think that aesthetics is very important for mathematical results and for mathematical research. There are a lot of applications of what I can show here, in particular for safety zones in industrial plants. So you can see on the picture on the bottom right that where there are industrial plants with a lot of robots, so you have marks on the floor in order to be sure that human beings will not be hurt by robots. And despite the famous law of robotics, where a robot cannot hurt a human, anyway, we have to be prudent. So we have something like that. But we have also a lot of reasons for education. Because teaching mathematics was traditionally about the first definition and then theorem and proof of the theorem and then sometimes examples. But now, using digital technology, we can go in a reverse direction and make mathematics and experimental work. The laptop or the computer began to be our lab. And so we can have another approach via exploration and then experimentation to arrive to conjecture, and then we are trying to prove them. And the proof can be written by hand, pen and pencil work, but the technology and the mathematical software like Maple is very, very useful for that. This is also a way to attract students to a way of thinking closer to the way a researcher is thinking. And probably also we have to look around in the modern world where everything is done via a screen, even to buy a plane ticket or a train ticket, and everything is made like that. But what is important for us is that we have a shift toward an active learning and discovery of things. The example that I want to show, but it's only an example, is the example of envelopes. An envelope of a family of parameterized curves in the plane is a curve, if it exists, which is tangent to every member of the family. For every member of the family, the tangency points in a different point from the others. This is what Koch calls an impredicative definition. It's very hard to use that. We can have a presentation, a graphical presentation of that, but to use it in order to define an envelope is very hard. And among the 4 different definitions of envelopes which are not equivalent. There is one which is analytic, and sometimes in some books, this is the only one which is presented, but it can be derived from the predicative one. And if you have a family of curves given by an equation f of x, y, k equals 0, where k is a real parameter, then an envelope, if it exists, is a solution of this system of equation. F of x, y, k equals 0, and the first derivative with respect to the parameter equals to 0. And the way we can do that is a multiple way. For example, here on the left, it's a first exploration doing by hand, using the hand and the mouse with a software called GeoGebra. It's a dynamic geometric software. And then using your hand, you can have a kind of approximation to have a look at what happens. And here we had a deltoid and a family of circles of equal radius centered of the deltoid. And using the mouse, we could move the circles and have the impression that there should be something there. There should be an envelope with these arcs and half circles and so on. But by that way, we have a graphical visualization. We don't have an equation for the envelope. In order to have equations, we have to solve this system. And solving this system will yield a parametric presentation of the curve. And generally, it will lead a union of different arcs with the different parametrizations. Then we will see later what we do with that. On the right, it is a visualization, but dynamic, but it has to be programmed. It had been done with Maple. And what you can see is the dynamical presentation of the circles centered on the blue deltoid. And actually, here you can see what I said when I said that we will have several parametric presentations, because solving this system of equations with a regular solve command, we obtained 2 parametrizations. One of them describes the red part, and the other one describes the green part. But at least here we have something quite precise and interesting, and then we can go further. This is the code that we had to write in order to have this animation. It's not a very complicated code, but what is interesting is that when we are solving using the solve command, we obtain parametrizations. But sometimes, for some goals, we don't want a parametric presentation of the curve. We would like an implicit one. And then we have to use another package, a package for Gröbner basis. This is purely algebra. I said that we have an interplay between geometry and algebra. And so we could, in this case, transform the parametric presentation into polynomials, and then using this polynomial ideal package, this is the name, we could define a polynomial ring generated by these 2 polynomials that we computed, and then by elimination of the parameter, we could obtain an implicit equation. What is important is that we could factor it, but actually the answer was that the polynomial is irreducible. And then we know that this very nice curve that we obtained there is irreducible. That is to say that the different components that parameterization is giving are not given to distinction by algebraic means. So this is an important case, and we have a related topic, which is offsets. I should mention that, for example, something very, very fashionable today is to use AI. And if you are asking AI, and some of my colleagues did it, asking for envelopes of a family of circles on, and the AI answered that this envelope is actually an offset of. This is totally wrong. In some cases, you can describe envelopes and offsets by the same way and the same curves. But for example, as soon as a progenitor, the basic curve in the example, it was a deltoid. As soon as this curve has singular points, the envelopes of circles of radius r is different from the offset at distance r of what we are doing, and the offset will be much smaller. And even if the envelope and the offset both have singular points, what you obtain, it's totally different. Here we have also some kind of visualization using the normal vectors to the ellipse that we have here, and we can have some impression of what will be obtained. In that case, we can make some kind of experimentation in order to have a look of what can happen. So it can happen if you have an envelope of circles of small radius or the offset at a small distance, maybe you don't increase the singularity of the curve. And in this case, we have on the left, we have an ellipse, and the envelope of the circles of radius, given radius here, 1, is the union of two loops, of two components. Once again, we ask AI to say what we obtain, and the AI answered that the offset of the envelopes that we are computing is an ellipse. This is wrong. We have two components, none of them is an ellipse, and they are not distinguishable by algebraic mean. The polynomial that we obtain is irreducible. But if the distance is small enough, we have a smooth curve. If the distance is larger than a certain limiting value, then we can have cusps and we can have self-intersections. In a lot of examples, tens of examples exist for that. And once again, we had to try and to look at that. So we had an experimentation using GeoGebra Discovery. It's a free downloadable software, but we wanted to be more precise. And then we had to look for the singular points of, and this is what we had already for an envelopes of circle center on the Keys curve and for offsets of the Keys curve. That's what you can see on the right. And this is what we obtained using Maple after we made the complete computations. So the Keys curve is here in purple, and we obtain the envelope by two different parametric presentations. But when we are implicitizing the curve, the parametric presentation we obtain for both parametric presentations the same polynomial. This is not a surprise because we are working in Zariski topology, and what we had, the only one component is not enough in Zariski topology, and we have we are computing a closure of what we can see, and we wanted to define the curves, the cusps, and to define the points of self-intersection. It was not so easy, but for the cusp we could use different methods, at least two different methods that we programmed using Maple. And here you can see some examples at various distances. And so here we could have some kind of definition using only the normal vectors to the curve and the sheer definition of an offset. But we could find the cusps of the curve using the curvature. This is more rare to use the curvature, but it worked very well. And we obtain all these nice curves that you saw using both methods, but the method using curvature was more efficient, or at least we arrived to what we wanted much earlier. What we could do was also to look for self-intersections. And we could do that, we could find, but you know that when you have a parametric presentation, to find self-intersection is quite complicated, but we were able to do that. And you can see this on the figure here. What we have here, and we had to solve this problem, is that at first there appeared irrelevant segments here. So sometimes irrelevant segments or irrelevant components appear because of this closure in Zariski topology, but here it was not the problem. The problem was our usage of the software and the intervals that we have here on the left bottom, the intervals that we choose in order to plot the different curves were incorrect. And so we had to make some fine tuning to reduce the intervals until we could obtain intervals where these irrelevant segments didn't appear. But we did it, and in the paper, it's well done. So as a conclusion, we have some kind of very important issues. It's important to define these curves, these envelopes or these offsets. For some goals, it's better to have a parametric presentation. For some other, it's better to have an implicit equation. So we have to try both. And in order to find singular points, actually, using an implicit equation can give you the singular points, but not a very, very efficient method to classify them, to know which kind, and even curves. There are two kinds of curves and so on. And so in that case, it's better to work with the parametric presentation. So we have a lot of important issues. The problems with implicitization is that a lot of time, the degree of polynomials is very high, and we can use the implicitize command in Maple, but in that case, we have to have a good intuition in order to define at first what we think to be the degree of the polynomial we are looking for. But we can do this. This is this is an algorithm which has been developed a lot of time ago by Elias Gutierrez and Rob Corless and Stephen, so it works. But when we are working with students, I prefer to push them not to use an existing command as a black box, but I'm trying to have them understand a little bit what is behind the command, what is in the box. And so after they know something, I can present this to them. Actually, we have a lot of challenges in what we are trying to do. We are doing, let's say, I have around me in JCT at least 3 pairs of colleagues or students who are working in this area, in this domain of knowledge, but in different directions. And actually, what is behind all this is what I said at the beginning. I think it's very nice, it's very pleasant. And actually, when I was a beginning PhD student, the director of the lab said it when somebody asked, okay, we saw now the theorem, what are the applications? And the boss answered, it's a new theorem. We saw a proof. This is nice to see, that's enough. And so this can be also a good motivation to do things. So actually,
if you're okay, could we move over to some questions now, Thierry? Is that okay?
Yes.
I think
yes,
you had
just one sentence with your permission is that this interplay between the dynamic geometry and the computed algebra system that we can have, these give a very rich environment in order to explore and to be able to prove new things. Thank you.
Thank you very much. Just an angle. So if you have a question for Thierry, please unmute yourself at this time. You could ask it directly or type it into the chat. One of the slides showed about implicitization. Was that a lot of heavy lifting when you were doing the equations and the research? Because some of that was manual rather than being able to use Maple.
Yes, I showed that in a manual way. It's sometimes possible to shorten, but not always, because it depends on what you have in your parametrization. For example, if you have a trigonometric parametrization, so you have to transform it into a rational one using very simple formulas expressing cosine and sine as rational functions, and then you have to transform this into polynomials using only the numerator. If you have an irrational parametric presentations, so you have to square it. For example, if you have square roots, you have to square it, but you may have to square more than once. And then, of course, the degree of the polynomial is increasing very, very fast. And by the way we did it, and we try to remain in control of what we are doing, and some of the actions that we did could be more automized, and but we prefer to do it by hand in order for the students to be able to follow what we do.
For sure, yeah. There was one question that's been typed into the chat. While this example has focused on 2D geometries, do you expect in the future to see the use of this geometric models to 3D? Certainly there are some...
Finitely, yes.
Right.
We
they
began.
mentioned some
We began already.
Tools.
And actually, we're in one of the examples that we have, but we didn't publish it yet. I think it will come. We could have a very nice mathematical model of a jellyfish landing on a clam. So as soon as we are going to 3D, we can have some nice imagination of what it represents. But definitely, yes.
And another question just came in. Another comment just came in. Are you familiar with geometric expressions as another package that works with
no, not yet.
DGS?
No.
But if you want to add a comment.
Actually, I downloaded it to my computer, but I didn't begin learning it.
Right. Well, thank you very much for your presentation. That was a really good summary of so much work, but also gave us an update of where your team is at. And we've even seen some of the work referenced in other talks. So it just shows you how much is progressing in that area today. Thank you again.